So thank you very much. I mean, I want to say really thanks to Mushin and John particularly for organizing this school. I know it's a huge amount of work. So my goal is to present, as the slide says, a pedagogical overview of quantum evaporation of black holes from the loop quantum gravity perspective. This is not meant to be an exhaustive treatment. I mean, just 2 hours. Rather, this is the important point. I hope to convey to you what the conceptual issues are and what the viewpoint of loop quantum gravity on them is. And I would like to distinguish between concrete results and expectations and hopes. And I trust that this will complement the other lectures. So my lectures, I'm not going to try to cover something that happened in the last 2 years, last 1 year. A lot of students here, I feel, need the background as to what the issues are, and that's what I'm going to really talk about. And also, I'm not going to be talking too much about astrophysical applications. Over the years, both in loop quantum gravity and outside, there has been great excitement that perhaps for good reason, that quantum gravity effects can be seen in astrophysics and gravitational waves and so on. And those things have all sort of really faded away. So that doesn't mean that people should work on them. Of course, people should work on them. But for students, I think they should be aware that these waves have come and gone, many of them by now. And I think it is good to understand what the basic issues are, and then you can decide what you want to work on. And I trust that these will complement other lectures. As you will see, the general picture is rather clear, but many issues remain open. And this makes the field attractive for younger people where they can contribute. And this talk will serve as a background to particularly to the plenary lectures. There are going to be 4 plenary lectures on black holes. And so this is the idea. It really is based on many people's work. And in the slide, I'm not going to be overcrowding with too many references. There are some references that came up because I took the slides from some other talks. But I'll give you, for students, there will be a list of references topic by topic, so where they can learn more about what I'm talking about. So the lecture 1 is going to be on conceptual framework, the main issues and the loop quantum gravity viewpoint on them. And then on the second lecture, I'll talk about the overview of the semi-classical approach, singularity resolution, and of black holes, and the current status of the information loss issue up here. So let me begin at the beginning, literally, and I think all of you, I hope, have seen this Penrose diagram. This is a classical collapse. We've got a star up here, which collapses and forms a singularity, and then there is an event horizon up here. And we can see from this diagram that if you give me some data on Scri minus, some quantum field, or some data of a classical or quantum field, then the state would evolve, and part of it will go to Scri plus, and part of it will fall in the black hole. And therefore, while Scri minus is a good initial data surface for zero rest mass fields, Scri plus is not, because some of the information classically fell into the black hole up here. Just this remark that very often in the popular or even technical things, people say that this is related to the black hole uniqueness theorem. You can form black hole in many ways and so on. And that is not true. The black hole uniqueness theorem fails in many instances, but these paradoxes that we are talking about are true even for them. So really, this has very little to do with the black hole uniqueness theorem. It has just to do with this causal picture that we're seeing up here. Okay, so now this was classical theory. Now we want to go to quantum field theory. So what in the celebrated work in 1974, so exactly 50 years ago, what Stephen Hawking did was to say that supposing such a black hole is formed, then I give myself a vacuum state of a quantum field of the Scri plus, or Scri minus up here. And in the Heisenberg picture, what is the interpretation of this vacuum state as Scri plus? Now the statement is that if you look at the observables associated with Scri minus and Scri plus, Scri minus the observables will form a complete set for this field, but at Scri plus they don't. And therefore I have to trace out the degrees of freedom on the event horizon, and as a result you get a density matrix, even though the total state is a pure state. Because I traced out, because of the event horizon, I get tracing out those states on the event horizon, I get a density matrix here, which appears to be thermal. But it's important to realize that there are 3 assumptions up here. Namely, the space-time is treated classically. So there is a star which is collapsing to form a black hole. Then the quantum field is a test quantum field. So Hawking ignored the back reaction of the quantum field on the geometry. And the third thing is that the matter field, and this is important, this is not really taken into account in many, many presentations, that matter field which collapses is classical and distinct from the rest of the field considered. So when you consider the star like that collapsing, or data is coming in from I minus, it's not a closed system. And therefore the issue of unitarity cannot even be asked really for the system. You need a closed system for that. And that is really a flaw of this picture, and that is repeated in many, many arguments later on, because we don't take into account the quantum states of the star, which is coming in at I minus, and therefore it is not really registered here. What we want is a closed system, so we'll see how to make a closed system later on. Okay, and then if the incoming state on sky minus is vacuum, then the outgoing state is a mixed state, which is like late time thermal. Now, what about including the back reaction? So black hole is emitting this quanta going out to infinity, and because of that it is losing energy, and therefore the geometry outside must change. So what about that? And in his 74 paper, Hawking just wrote down this diagram based on the assumption that over here we've got a classical singularity whose strength is given by gm upon r cube. That is, for example, the Weyl curvature behaves like that. And as the mass goes up, so mass goes to 0, so m is in the numerator, therefore the strength of the singularity diminishes, and when the black hole has completely disappeared, then the singularity would just stop. And therefore, since there is no mass up here, Hawking just drew on this bit of Minkowski space to space-time and proposed this as a picture as a Penrose diagram for the semi-classical evolution of the black hole up here. But now in this picture, because we got a singularity in the future up here, it is still true that information which goes in here, some of it will go into the black hole and some of it will come out, but because there is singularity, it's clear that there's going to be some information loss. So in the general relativity circles, there's an agreement that if in fact this picture were the correct picture, then information will be lost. We cannot get information at sky plus completely. However, in string theory communities, it is felt strongly, based on ADS-CFT correspondence, that the reciprocal matrix is unitary and therefore information is not lost. Well, if it is not lost, then what, there's a problem, right? So the idea is that somehow as the black hole evaporates, quote unquote, the information that was lost, the Hawking modes which fell in, that is the information that is lost. These modes are correlated with outgoing modes. So these modes, outgoing modes are coming out. But somehow then the idea is that there should be some mechanism by which the information is restored, even by this time up here, so that the state here is already pure, because to the future, it is argued, there is just Minkowski space, and therefore state here should be pure. And therefore, there are many proposals as to how to get this information out up here. There are fast scrambles, there are firewalls, there are many, many things that are proposed, double copies, quantum Xerox machines, and all of these ideas are no longer pursued. And the failure of semi-classical gravity, because something is wrong here in the semi-classical region up here, and these ideas have really been now more or less ruled out by LIGO observation. So the idea that the information should come out up here is a strong belief in some of the communities, which is not shared in loop quantum gravity. Now there are three drawbacks, which when corrected lead to a completely different space-time. And this lecture is complementary to what Carlo was saying yesterday. The overall pictures are the same, but the details differ. And also the emphasis is different up here. But it makes a whole package. The three things that in loop community one says are the following. The first is that the heavy use of the event horizon. Here is the event horizon. It's an absolute boundary. Things from here can never communicate to outside. So the heavy use of the event horizon is inappropriate and misleading. Already in classical general relativity, as we will see, event horizons, which I will call as EHS, have severe limitations. Namely, we'll briefly, to know if a space-time admits an event horizon, you need to know the entire space-time to the infinite future. But for an evaporating black hole, we don't know that. That's what we are trying to determine. So we can't know where the event horizon is. Second, the event horizons are teleological and ghost-like. This is literally true according to classical relativity, that event horizon may be forming and enclosed in this room right now and growing in area because of a gravitational collapse that would happen a billion years from now somewhere in the center of our galaxy. So they're really ghost-like, and therefore they really don't have any such a direct physical interpretation. And there are more appropriate notions. These are quasi-local horizons, and these were introduced among other people by our chair, Chris Bittle. There's a whole group of people in Penn State who introduced these notions. And in particular, there are dynamical horizons, and this is shown in the picture. So now what I'm doing is, I told you that there is a flaw in using this kind of picture with a star, because you can never have unitarity, because there are quantum states of the star which are not really registered on Scri minus. So instead, what we're going to do is to have a collapse of a null scalar field or a null fluid from Scri minus. And now all the states are really are included in the picture. So this null scalar field collapses, and the scalar field also, or zero rest mass scalar field collapses, and the zero rest mass scalar field is also Hawking emitted up here. So we've got a closed system, scalar field and gravitational field of classically Einstein gravity. So in this case, in the classical picture, in this whole region, space-time is flat, the scalar field falls up here, and in the future, it is Schwarzschild. And indeed, if I look at the event horizon, then this is the event horizon, and you can see that the event horizon starts forming in the flat region of space-time and grows. This is what I was telling you. It might be growing right now in this room. This is what is happening up here. It starts and grows up here in a completely, this whole region of space-time is flat, and it is really growing up here. And just more recently, for those who are mathematically inclined, there's a very beautiful work by these people. It has to do with showing that the third law is wrong, is incorrect. Rigorously in classical general relativity, they show it's incorrect. In that picture, they have more examples in which the event horizons are really unphysical, because they really start forming in the flat space-time and then grow. So we're going to say that this more appropriate notion and the dynamical horizon. And what is dynamical horizon? In this picture, I'm going to explain it in detail, but in this picture, in this collapse, dynamical horizon falls from here. It is space-like, it grows in area and joins on to the isolated horizon, to the event horizon, which is an isolated null horizon. It's also called isolated horizon up here. And the dynamical horizon is this picture, and they are quasi-local, so I can look at the geometry in this room and tell you that there is no dynamical horizon contained in this room. Okay, and then during the evaporation process, the dynamical horizon becomes time-like. So here is a classical picture up here, then here is a black hole evaporation. This again flat space-time. We're going to collapse of a null scalar field up here, and dynamical horizon forms up here. Here the dynamical horizon formed, and there is no Hawking radiation, so it just joins on to the event horizon. Here the dynamical horizon forms, but instead it bends over and becomes time-like, not null. And there is no event horizon, but this is a quasi-local horizon, which is also a dynamical horizon, and we'll see this in a little bit detail more. This is the first brush through it. And so the picture that you get is really this, and I've cut it off up here because I'm just looking at the semi-classical and not full quantum theory. So the figure shows a part of space-time where semi-classical description should be an excellent approximation. So for example, a solar mass black hole is formed by collapse. It evaporates under it has a lunar mass. And if it has lunar mass, it's a macroscopic object, and therefore you would think that semi-classical gravity should be valid. I strongly believe semi-classical gravity is valid, and none of the funny, surprising things happen up here. And therefore, during this process, in this process, when it is formed, the dynamical horizon in area grows. It is difficult to see, these are conformal pictures, but the dynamical horizon is growing up here, and then it becomes time-like, and then the area shrinks up here. Here it is, for a solar mass black hole, 3 kilometers, and here it becomes about 0.1 millimeter. But throughout this process, semi-classical gravity should be valid. And these two portions of dynamical horizon enclose a trap region. So in this region, if I look at any light front, then that light front is always going to be contracting. Both outgoing and the ingoing light fronts are contracting. Now, what we are going to see is that the space-time geometry in this trap region up here is highly non-trivial. Carlo already alluded to that, but there are really calculations in detail which show that this is the case. And this is counterintuitive, very counterintuitive. But this time scale is huge. It is 10 to the 67 years. Universe is, a billion, 14 billion, so 10 to the 10 years. So this is really 10 to the 57 times the age of the universe up here. So this is a very long process, and during this long process, if I look at space-like surfaces which come in like that, and if I just look at the region of the space-like surface, which is enclosed in between the dynamical horizon, the length of this surface, so it's S2 cross R, it's 2-sphere cross R. The 2-sphere part doesn't change very much. From here it is about a kilometer, about a 0.1 millimeter, and over here it is going to be about a kilometer. So from 3 kilometers it will maybe shrink to a kilometer size up here. But this length grows astronomically to about 10 to the 63 light years. So it's really huge. I mean, it's many times the radius, the size of our observable universe. But of course, this also is many times the history of the universe. And therefore, the statement is that this picture is completely different from what Hawking and other people were considering when they're looking at this picture up here. So that is the second point. Quasi-local horizon is the first point. The second point is that the geometry of this region is very non-trivial. And the third point is that in Hawking's picture, singularity remains. And this is a picture that is used by many people. I think it's just not correct, as Carlo also said yesterday. But the question then is, what happens to that singularity? Here, I just cut off space-time here. What happens if I were to extend the space-time future? So the statement up here is that, in fact, there is a singularity resolution in loop quantum gravity. And since not everybody here is familiar with that, I'm going to go into it a little bit detail. And this occurs because in loop quantum gravity, I'm going to explain this also why. There is a smallest non-zero eigenvalue of area that you heard about from Christina probably, which is about 5.717 times Planck length squared. And because of that, it turns out that, and the curvature operator is defined in terms of not taking the derivatives of the gravitational connection, but is defined by looking at the holonomies, the Wilson loops of the gravitational connection along a closed loop. So I go along a closed loop like that, and I look at the Wilson loop, and then that I know is given, like in the electromagnetism, this A dot dl is given by B dot dx. So similarly here, the holonomy of the connection along a closed loop up here will be given by some the curvature flux through here. And the statement is that that curvature flux is what we're looking at. And then you shrink the area of this loop, divide this by the area, and shrink the area of the loop, but not till the area goes to 0, but until the area becomes the area gap. And when that is the definition of the curvature operator, it is intrinsically non-local in loop quantum gravity. And this non-locality then, but of course only at the Planck scale. And in Param Singh's lectures tomorrow, you will see that in LQC, as a consequence, there is an upper bound on all physical observables. There are no singularities, and singularities are really resolved. And this is true for all strong curvature singularities in loop quantum cosmology. In the black hole, this is the critical picture that we got up here. The relevant part is really this part 2. Here is the singularity up here, because that is the part that can close the singularity. And what happens is, this is the same picture up here, where I got the part, this and this are the same pictures up here. And what happens is that instead of singularity, you have a regular surface up here, which is a very peculiar surface that I will talk about. It's called a transition surface tau. To the past of this transition surface, the geometry is more or less like here. These regions are trapped. In other words, if I take any 2 sphere here and I shine light, both the outgoing light front and the infalling light front are contracting, whereas to the future of the surface, both of them are expanding. It's anti-trapped. So light here is coming out up here. And so this is what happens. The singularity is actually resolved. And as a result, space-time is bigger than what we had thought. So space-time here is bigger up here. We can evolve. Or this picture is incorrect. The quantum space-time is actually larger. We can evolve through up here. So this is the main point. And in the rest of the 2 lectures, we will see in detail, some detail, how these 3 novel features, quasi-local horizons, the non-trivial geometry in this trapped region up here, and then the last thing is the singularity resolution and the quantum extension. These 3 features introduce a profound revision of the original Hawking paradigm, which is depicted here, and it is replaced by a loop quantum gravity paradigm. And these 3 diagrams are taken from a paper written exactly 20 years ago with Martin Boyewald. And in fact, you saw these 2 diagrams, actually all 3 of them, in Carlo's lectures yesterday. And they suggest that Hawking's original proposal left should be replaced by one of these 2 things. That is what this paper suggested. And now, a lot of work has happened since then, of course, and some details. I mean, this is a paradigm. This was called the paradigm, the LQG paradigm. And this paradigm now has been developed in sufficient detail by various people. And the preferred picture I would like to claim is, in fact, this one. The preferred picture is this one and not this one. This is a picture, in fact, if the black hole evaporation time is infinite, this observer already has infinite proper time up here. Whereas in this picture, the observer infinite time-like picture is like that. So we will have singularity up here, and there will be some radiation coming out here. And this is what we want to understand. What is the current status of these pictures which are drawn 20 years ago? Okay. So this is the outline of what I want to communicate to you in detail, and I hope you have absorbed it. And if you have questions, please, detailed questions, let's have them during the breaks or where we, please feel free to come and ask me anything you want. But if you have clarification questions, ask them also during the talk itself. So now we're going to see in detail, so quasi-local horizons. So normally, what happens is the following. Supposing I got a 2-sphere, a surface of a 2-sphere, and I instantaneously light it. Then there is a light front which goes out, and there is a light front which contracts, which goes inside. The area of this light front is growing. The area of this light front is contracting. So one says that one has the outgoing light front and the ingoing light front, and the ingoing one is contracting, the outgoing one is expanding. And so this is what one happens, that these light cones are bent because of massive object. This is a star which is collapsing. Light cones are bending up here. And this is the surface at which the outgoing light front is so attracted by the mass that it's trying to escape, but it cannot. It is just frozen at that point. And this is called then a marginally trapped surface, and this is then the world tube of the marginally trapped surfaces that is formed up here. So it is much better in the causal diagram. Again, this is a star which is collapsing. I got outgoing light fronts, these are expanding, ingoing ones which are contracting up here. And now the event horizon is defined as follows. You go to Scri+, and you look at all of its past, and you look at the future boundary of its past, and that is the event horizon. So notice that you first of all need all of Scri+, and it is essential that the Scri+ be complete. Because, for example, by complete, I mean this affine parameter is infinite. Because if you allow the affine parameter to be finite, then I could take Minkowski space and cut Scri, cut on Minkowski, just cut Scri to a finite distance. And then I say, I look at the past of that, and therefore I got an event horizon, because past of that is not all of space-time, right? Even in Minkowski space, then there will be event horizon, which will be ridiculous. So it is really important that this Scri be complete. If it is complete, then you look at its past, look at the future boundary, and that is the event horizon. So the black hole region is the whole manifold minus, so this is set minus J minus is the past of light cone. So black hole region is therefore this region, which is removed, which is the one obtained in this particular way, and it captures captures the idea that the region from which light cannot escape. The null directions are all going to singularity, not to infinity. And the event horizon is the future boundary of the region from which light can escape up here. Now, event horizons have very interesting properties. particularly the laws of black hole mechanics. I just wrote them down. You can look at it later. You all know about laws of black hole mechanics. But event horizons also have serious limitations, and I already mentioned them. There is a teleology, namely an event horizon may be contained in this room, formed in anticipation of a gravitational collapse in the center of a galaxy a billion years from now. And to know if a space-time admits an event horizon, we need to know the entire future evolution and asymptotics. And it cannot be used in the numerical simulation of the binary black holes, for example. So again, this is a flat region up here. There's a null scalar field which collapses, forms a black hole, and dynamical horizon, as we will explain in a minute, starts out here and joins on here. This is completely physical, but event horizon is this past of sky plus up here, and this event horizon, you can see, really starts out in the flat space and grows in the flat space. And also, the role of sky plus is very global. There's an old PRD paper. I'm going to give references in the list at the end. So that will be available on the net, on the website of the conference. And Peter Hijack showed that, in fact, you can change the geometry, black hole geometry, in a Planck neighborhood of the singularity and make the event horizon entirely disappear. And so the event horizons are not to be trusted so much. But we have got quasi-local horizons. And the quasi-local horizons is this idea that you have got the light front which is going out, light front which is falling in. If the mass inside is strong enough, then the outgoing light front freezes. That two sphere for which the outgoing expansion is zero. It's not expanding. Its area is the same. And the incoming is negative. That is called a marginally trapped surface, or MTS. And this is the two sphere up here in this picture up here. Namely, you've got the light cones are such that the area along both null direction, the area is not changing along the outgoing null direction and is contracting, is becoming less on the ingoing one. And what you can now do is, in space-time, you can stack these marginally trapped surfaces together and form a horizon, and that is called the quasi-local horizon up here. And this is what numerical relativity people do. I work with them all the time in classical relativity, and we study the properties of these quasi-local horizons. Now, the Raychaudhuri equation implies that if the final dynamical horizon, in, for example, the binary black hole merges in classical relativity, there is a flux of radiation inside the horizon, and therefore the area of the horizon actually grows. So, then that quasi-local horizon is called is a growing dynamical horizon. It's space-like. When it is in equilibrium, like here, for example, dynamical horizon grows because matter is falling in. Then the infall stops up here, and therefore the dynamical horizon becomes null. So when it is when there is no influx of matter, it becomes the area remains constant and it becomes null. And during black hole evaporation, where the influx is negative, then the dynamical horizon becomes time-like and the area decreases. If the area is changing, then the quasi-local horizons are called dynamical, and if it is null, then they are called isolated. And there is no teleology, there is no dynamical or isolated horizon contained in this rule. And now, the laws of black hole mechanics, which made event horizons so appealing, are all true for dynamical horizons as well. And in fact, it's better, because Hawking's theorem about area increase only tells us that the area must increase of the event horizon. And as we see, there is no mechanism, physical reason for its increase. It can increase in flat space up here. Whereas for dynamical horizons, there is a law which says that the area radius R2 at a later time R2 minus at an earlier time R1 is given by an integral which is matter energy flux into the horizon and the gravitational energy flux into the horizon. So if this is really the flux is positive, then the area will increase. If this flux is negative, then the area can decrease. And therefore, the laws of black hole mechanics are also valid here. And then we also have, I put here things about isolated horizons. I have more slides here because you can look at it on the web later on to complete your information. We're not going to use isolated horizons. And there is also a comparison between event horizons and quasi-local horizons that you can look at more carefully in detail up here. So the summary of the part one is on the horizon structures is the following. Again, this is a white dash solution, this null scalar field collapsing up here, and this is a semi-classical solution up here. The left figure, the dynamical horizon forms because of null fluid or null scalar field collapse. It has zero area to begin with, and it grows until its area becomes equal to 2m, the mass of the total mass that has fallen in, and then it remains constant up here. When the collapse ends, it joins onto the null isolated horizon, which is also the future portion of the event horizon. And now the question is really what happens now in the semi-classical theory, because we got Hawking radiation. We got Hawking in flux, then what happens up here? And we're going to see that what happens in the picture I already discussed a little bit, but we'll see how this arises in some detail. So this is a semi-classical picture up here. And the right-hand figure says that now we switch on H bar, the quantum effect, and using semi-classical approximation, the growing dynamical horizon, this was growing up here from here to here, instantaneously, as soon as at this corner, when the incoming flux stops, the horizon becomes null, instantaneously becomes null. And to me, it was a delight to see some inexactly soluble models that we'll see in a minute, that in fact, the Hawking radiation starts at this retarded instant of time. Precisely when the dynamical horizon, in a prompt collapse, it starts precise. By prompt, I mean, you send in a pulse. You don't sort of send in, keep on sending pulses, but if you have prompt collapse, a star or some null fluid falling like that, so you got a sharply peaked the profile up here that falls in like that. In that case, the Hawking radiation starts exactly at this retarded instant of time up here. Up until here, there is no Hawking radiation is completely negligible. There is roughly one particle, one quantum that is emitted in all this time, and then the radiation really starts at the formation of this at this inflection point where the space-like dynamical horizon turns time-like up here.
Sorry, is that R equal to N?
This will be R equal to 2n, yes. Now, so that we switch on up here, and the Hawking flux starts at U equal to U naught, that I already said. Now the outgoing energy, however, now it continues, and therefore the outgoing energy at Sky plus is positive, and is compensated by negative energy flux. And this is not a fiction, this is not some general hand-waving argument. People have calculated in detail the stress energy tensor here, the renormalized stress energy tensor. You have to renormalize in quantum field theory in curved space-times, and which I have shown that in fact that flux is actually negative. And so it is compensated by this negative energy flux up here. And then the dynamical horizon area, because the flux is infalling flux is negative, energy flux is negative, the area starts decreasing. So this becomes time-like, and now the area is, this becomes time-like, and now the area is actually decreasing up here. So here it was increasing, here it is decreasing up here. So here it was, in our example, it was a solar mass, and here it is a lunar mass. So here it is 3 kilometers, the area, radius is 3 kilometers, and here the radius is 0.1 millimeter, about 10 to the minus 7. The lunar mass is about 10 to the minus 7, the solar mass. So this is what is happening. And then the region enclosed by these two parts of the dynamical horizon is a trapped region up here. This is a trapped region up here. And the statement is that and in this region, this is a trapped region because both the outgoing and the incoming light fronts are contracted in this region up here. And I cut off this statement, this space-time up here. This is called U equal to U naught. Here it is U equal to U last ray. LR is for last ray, because I just cut off the space-time when the mass becomes lunar mass, because I can trust semi-classical gravity here completely. We found that one can actually trust it until it becomes about 1,000 times Planck's mass. Yeah. So now let us discuss the inclusion of back reaction in the semi-classical gravity. That is the approximation in which gravity is treated classically.
But matter is treated quantum mechanically, and the two are coupled to each other by the idea. So you got a metric GAB, classical metric GAB. You got a quantum field phi hat. You compute the stress energy tensor, which is renormalized of phi hat. I should say renormalized stress energy tensor. And then you take the expectation value of this stress energy tensor, and you set this to be equal to 8 pi g times this to be equal to the Einstein tensor GAB of the classical metric. So this is completely classical. This is quantum mechanical. I need a state, and I need the renormalized stress energy tensor to calculate, and then this is the equation that I'm looking at. The matter itself satisfies a block of G, where G was determined by the matter in that. It's a coupled system of black, let's say equal to 0. In our case, it's a 0 rest mass field, so block of the block with respect to the metric G of phi hat is equal to 0, where G was determined by the previous equation up here. Now, okay, so this can be justified in what is called the large N approximation, where the number of matter fields is very large. Therefore, the quantum fluctuations of the matter field is very large compared to the quantum fluctuations of geometry, and that approximation you can trust the semi-classical gravity. And this is also called a mean field approximation for geometrical variables. So whatever metric is, or operators constructed from geometrical variables, they are replaced by the expectation values of the quantum operators. We don't know the quantum theory, but supposing we knew the quantum theory, then we're replacing that by the expectation value of those operators, and matter is treated as a quantum field. So geometrical operators are replaced by their expectation values. They all become C numbers. They become classical fields, and the matter is treated quantum mechanically. And we can proceed, therefore, in two steps. In the first step, I'm going to consider a simplified model where the results are completely known, but with a simplification which makes it exactly classically soluble. We'll see. It is not a stupid model. It is not something made so simple, so many assumptions to make it soluble that it is really not physical. It's very close to being physical, but of course it's not physical. It has some limitations that we'll see in a minute. Because what happens in this model is that you can actually first solve the general relativity equations, Einstein's equations coupled to the scalar field. We can solve them exactly classically. You don't need numerical simulations. So this is my favorite part. When I teach classical general relativity, I do this in a class, because in one lecture, it's a 1.5 hour lecture, you can start from scratch and show the students how the black hole actually, the collapse occurs, black hole forms, what happens, etc. And then one can first solve for, as we'll see how you can do it, you can first solve for the matter, and then given the solution, you can determine the gravitational field in this case. And therefore, what you can do is, because classical sector is exactly soluble, you can write down the semi-classical sector, but now we have to solve it on computer. And fortunately, I had the good fortune of having one of the best the numerical relativists in the world, Franz Pretorius, and his student Fethi Ramazanoglu, and therefore we could actually do high precision calculations. This model was analyzed by other people, including Hawking and Stewart, and by Piran and Strominger earlier, but their precision was not so good, so they did not get the physically correct answers. But in this case, with Franz Pretorius's extremely high precision, we could get good answers. So that is the first part. In the second part, we'll talk about the spherical collapse, and that will be in the next lecture. So let me begin with a simple model, and this is the following model. First, let's not worry about field equations. Let's just look at spherically symmetric metric and then a scalar field F up here. So spherically symmetric metric is going to be given by a metric in the RT plane plus the two-sphere metric multiplied by the radius square. And we're just going to write it as GAB always in this few slides, in this model, is going to be a two-dimensional metric. 4GAB is going to be the four-dimensional metric. And SAB is just a two-sphere metric, d theta squared plus sine squared theta d phi squared. Then if I just take this, and then the action, in the general relativity action, then the Einstein, the metric, and now what I'm going to write is this metric variable was four-dimensional metric. I'm replacing it by two-dimensional metric and R, but I'm writing R as e to the minus 2 phi. Phi is called dilaton field. It's just a substitution divided by kappa squared, and kappa has dimensions of 1 upon length. So I just do that. And then the statement is that instead of the metric, I get the two-dimensional metric and the scalar field, which is just the R squared, if you like. And then I also get the matter field up here. So in Einstein's theory, I get 2 here, I get 2 times e to the minus 2 phi here, and e to the minus 2 phi up here. So this is what is general relativity. The Callan-Giddings-Harvey-Strominger, or CGHS black hole model, the action they start out is inspired by something in string theory, but we don't have to worry about that. The action that they take is really almost the same. 2 is replaced by 4, but here is important. 2 to the e to the minus 2 phi is replaced by 4. And here is the most important case, namely e to the minus phi just disappears up here. Why is this important? Because in Einstein's action, we have got, of course, the geometrical field. Here, scalar field and the phi are coupled to each other, but there's a 4-dimensional, the metric and phi are, sorry, the scalar field phi and the 4-dimensional metric are coupled to each other. And here, the evolution of this scalar field is really has this e to the minus 2 phi, which is the geometrical part. But here, that geometrical part has disappeared, and therefore I just have this action. And now the statement is that we can now just take this f is a scalar field. Because this metric is 2-dimensional, I can just write it as a conformally flat metric. So the upstairs metric is omega times eta AB, and the gravitational sector then is going to consist of instead of, because I got eta already, so the information about G is all in omega, and then the information about R up here was in the dilaton phi. So the gravitational sector is just phi and omega. And the 2D and the 4D are very similar, but the CGHS action is much simpler because the matter field now satisfies, the action is just this, so the matter field now satisfies block of eta equal to 0, because the equation is conformally invariant, it just satisfies block of eta equal to 0. So we can just forget about the gravitational sector, solve for the scalar field, and given any solution, we can write down the solutions for the equations for phi and for omega. And if I take eta, the flat metric, to be expressed in the retarded and the advanced coordinates, retarded coordinate z minus, usually we call it u, advanced coordinate z plus, we call it v, then the statement is that I can, and also define x plus minus to be just an exponential of these advanced and retarded coordinates, then and I write capital phi to be equal to e to the minus 2 phi, and omega to be equal to just changing of variables, theta to the minus 1 phi. So instead of omega, I got theta up here. This is just change of variables. It doesn't make any difference. But the statement is that the solution can be just written. The gravitational part now is in phi and theta, and you can write down closed solutions. It's not important for you to understand this. It will be in the notes. You will see it, and there are references that you will see. So what happens is the following. Here is a flat space, and I give you some scalar field, 0 Reisman scalar field, falling in from infinity. It says solutions are trivial, right? Because there are going to be the right moving modes, and there are going to be left moving modes. There's a 2-dimensional system, so it's just t plus r and t minus r. And I'm looking at the left moving modes, and I'm just looking at that. It's trivial. But if you give me this, then I can actually find theta and phi and write the metric GAB like that. So if the metric is written like that, then where is the black hole? I got a metric all over the place up here. Where is the black hole? Well, what happens is that on a space-like line, the phi actually vanishes. Because phi vanishes, the contravariant metric vanishes, the covariant metric blows up, and we got a singularity. So G as a metric, the theta and phi are perfectly fine, but G as a metric is singular here. If you try to compute its curvature, it's singular here. So it is this space-time with the scalar field propagating is reinterpreted as the scalar field propagating, but as seen by the metric GAB. The scalar field satisfies the wave equation with respect to eta. It also satisfies the wave equation with respect to G. But G has a singularity eta does not have. So that is a funny thing, that we got a black hole because the physical metric is G. That is what the theory tells us, and not eta. That is why there is a black hole up here. Theta and phi are perfectly fine, but as a metric, G is singular up here. So these are smooth fields, but the interpretation is that G is a physical metric that determines the space-time geometry. And the same phenomenon for the Hawking effect if you look at the background mg. So now supposing I actually send in this pulse, right? I mean, the pulse is really given by any f plus is just any function of z plus, right? If z plus is moving up here, the retarded time, any function. So I just make a function like that, and that's it. That's the solution up here. Given that solution, I solve for theta phi, therefore I solve for the metric, and I get this black hole. Now, for the Hawking effect, I'm going to take f minus, and I'm going to consider the quantum field f minus, and I'm going to give you a vacuum state of this quantum field up here. Now, this is the same as giving the quantum field up here. The propagation of the scalar field on this spacetime and on this spacetime is the same, so I can just propagate it. And of course, this is a trivial field, free field theory in two-dimensional Minkowski space. So here I get vacuum, and of course here I'm going to get the same vacuum state here. Nothing happens up here. So if I start out here for this f minus, then if I start with a vacuum of this f minus, then I will just get vacuum state up here. However, for the physical space-time, the physical space-time ends here. So this is not part of the physical space-time. Therefore, I have to trace all these degrees of freedom, these modes of it. When I trace all these degrees of freedom, amazingly, it's a fact that what you get up here is precisely a thermal state as in. So nothing, I mean, it's trivial exercise. You can do it in class, and namely, it's really free field going from here to here, but I got Hawking radiation just because I just trace over this thing. Now, here is the important point. This space-time does have an event horizon. Sorry, this space. Yeah. This is a classical space, right? This classical space-time, this is a classical space-time. That classical space-time does have an event horizon because you can calculate the affine length up here. With respect, if I calculate the affine length with respect to the Minkowski metric, it will be finite. It will be finite up here. And if I calculate with respect to the physical metric, it's also finite. So therefore, this actually does have an event horizon, and I got a singularity. And therefore, here, Sky plus here is complete for Minkowski space-time, but this Sky plus is complete with respect to the physical space-time. That is an important point up here, and that is why I got an event horizon, and I got a black hole interpretation. Okay. Now here, what I would like to now do is semi-classical approximation, and that is called the mean field approximation. So I told you, what did I tell you so far? That you can form a black hole. It's trivial. Mathematical calculations are trivial. And the whole difference is in the interpretation of this geometry. If you say the physical metric is eta, there is no black hole. If you say the physical metric is g, there is a black hole, where g is determined by this f plus via theta and phi by solving these equations. And as you can see, theta and phi are all expressed in terms of f plus and f minus. The details are not important. Conceptual structure is what is important. But really, details can be done in a class, in a couple of classes. You can do the semi-classical approximation completely. Okay. So now what we want to do is the following. So Hawking contour going out up here, and I want to take into account the semi-classical reaction on this black hole. What happens if I take the semi-classical reaction? How does this space-time change? What happens? We saw that we expected space-time to change from here to here in the semi-classical picture. Does something like this happen? That is what we want to see. Okay. So again, the equations are not important. Their structure is. There's a framework for even full quantum gravity that exists. This was introduced with Tavares and Varadarajan, quite some time ago, 10 years ago. But the mean field approximation also was proposed there, and then, as I told you, that these equations were solved on extremely high precision computers by Franz Pretorius and Fethi Ramazanoglu. Without them, we could not have reached this conclusion. So first of all, we consider large number of n matter fields, and we look at the expectation values of the gravitational operators. Remember, the metric G is given by theta and phi because we got eta. So theta, phi, and eta is fixed, it's kinematical stuff. So theta and phi are the things, and therefore their expectation values you take, And so we have got the quantum field f hat, and then I take a compute. I compute theta, phi hat and theta hat from f hat and take just the expectation values. And now they are included in the back reaction. So this just satisfies the wave equation in Minkowski space-time, which is the same as wave equation in this physical space-time. And now we have got this equation. Right-hand side was 0 classically, but quantum mechanically now there is a stress-energy tensor. And it turns out that this stress-energy tensor can be determined analytically because of trace anomaly in the conformal anomaly or trace anomaly in the field theory that we have got up here. So you can compute this explicitly, and these are the nonlinear coupled equations you have to solve. This I cannot do in a class. We needed Franz and Faithy. And there are also constraints which you impose. So these are the evolution equations, and there are constraint equations which you impose on Scri minus. And the mean field metric is given by this. And the task is to solve these equations. And the global issues are, does GAB admit a Scri? Is it asymptotically flat? Is there a Bondi flux at infinity? What is the Bondi mass at the end of the mean field approximation space-time? Is it large? Is it Planck scale, etc.? So this is the classical picture, and the semi-classical picture is like that I will explain in a minute. So this pulse up here that is falling in is really this green line pulse that I have shown up here that is falling up here. So here classically you've got a dynamical horizon joins onto the event horizons. Here we've got a dynamical horizon. It joins onto another branch, time-like branch of the dynamical horizon. And then there is still a singularity, but it's a tame singularity in classical. So I should write it explicitly here. There is a tame singularity, because the metric here is regular, is continuous, but it's not differentiable in here. So in that sense, the singularity is actually tamed up here a little bit. Okay. And so the semi-classical part is just this part up here. Matter is falling in, horizon forms, horizon evaporates until, if you like, it reaches lunar mass. Here we stopped here at some stage, and then there's a last ray which goes out of here. So the space-like singularity persists, but is weak. It is only, the metric is C0 but not C1. And also this singularity ends here. Here the singularity went all the way to Scri, here it ends. And there is a last ray which can emit up here. Now Hawking and Stewart had claimed that in fact along this last ray there will be a thunderbolt singularity. And this thunderbolt singularity is kind of the precursor of the firewall that we heard about on string theories a while ago, firewall up here. And we find there's nothing singular here at all. The metric in this region up here is completely smooth. There's no problem at all. This is something that I could not have done. We really needed Franz and Faithy, extremely high numerical precisions to say that. Also ends because of evaporation, and that is to say it does not reach Scri up here. And along the last ray, the future boundary, this is the future boundary of the mean field approximation. And now we are going to ask the question. Over here, Scri was complete in the classical picture. And therefore, I had an event horizon, and this was the black hole region. What about here? I got a semi-classical metric now. So I can calculate, is Scri complete here or not? If it is complete, then this is a black hole region. I cannot continue. And we find it is not complete, exactly as we had hoped, or well, I had hoped. So in the classical space-time, this is complete, but in the semi-classical space-time, until the last ray, this is not complete, and we find out exactly how much it is. So there is no event horizon up here. Otherwise, the information would have been definitely lost. Furthermore, Ritchie's scalar and the curvature up here is completely finite. The singularity, there is a C0 singularity, the metric is C0 here, so the curvature is singular up here, but this singularity does not propagate in the semi-classical space-time. It does not propagate along this last rate here, last ray. So the gravitational collapse, this is the summary. Gravitational collapse of massless scalar field gives rise to a black hole. Model is exactly soluble in classical theory, and the Hawking effect is realized in the external field approximation. Again, there is a thermal flux at late times. Back reaction has been included through detailed calculations using a mixture of analytical and high precision numerical simulations. And the examples of results are singularity is tamed by back reaction, the physical metric is continuous there, and the metric can be continued across the singularity. Furthermore, the singularity stays well away from scry. There is no thunderbore, there is no firewall, and across the last ray, what forms and evaporates is a dynamical horizon H. There is no event horizon in the semi-classical space-time. And there are detailed correlations. This I was extremely happy to see, that there are detailed correlations between the area of this event horizon, of this dynamical horizon, and the bonding mass here. Extremely detailed correlations appear. And these detailed correlations are going to be important in quantum theory, in full theory. This is an open question that I will discuss a little bit in the conference up here, in the next week conference. So detailed correlations, and so we see that this is a back reaction in action. Okay, so here I've included a few other things. There's a real issue up here, namely in the literature, the bonding mass formula was incorrect, and therefore in the literature, if you use the value in the literature, it looked like the bonding mass was getting negative, and then there was instability, and what was happening there, et cetera, And in the paper with Tavares and Varadarajan, we gave the correct bonding mass formula. Bonding mass remains positive, and it is the correct bonding mass that is correlated with the area up here. So the horizon observables are correlated with the infinity observables. That is what we need to study more detail about loss or not loss of correlations up here. Okay, so I'm not going to go. And there is a certain beautiful universality in the dynamics. By the way, here is a plot, here the area and the bonding mass, and you can see that it is actually correlated. These are different colors are black holes with more and more mass. Here is more mass, here is less mass up here. And this is really close to the Planck regime. But still, there is a universal curve, and in fact, all these curves join in on this universal curve. There's universal relation between the area and the bonding mass. I'm not going to go into that in detail. And there are some challenges for mathematical relativists that you can look at. Okay. So this is my next lecture. So I want to end here.